Hello and welcome to Physics for Play. In this video, we're going to be examining why you have to be careful when you're using complex exponentials to solve nonlinear equations, and why you can't just assume that the real part of the solution is the only one that matters. Let's get started. What does any of this have to do with solving linear equations? Well, last time, when we were looking at the solutions to the simple harmonic oscillator equation, we made a few different ansatzes, different guesses for what the solutions were. We showed that those solutions work. Those solutions generally all involved trigonometric functions, some linear combination of sines and cosine functions. And it turns out there was another way we could have written this solution. So we could have said x of t rather than writing it out in sines and cosines. Well, since e to the I theta can be written in terms of sines and cosines, we could have written the solution instead of in sines and cosines. We could have written it as an e to the ix. So I could have said this is e to the, let's try that again. We could say that this is e to the power I times omega t plus some phase shift. Because again, e to the ix is essentially, or e to the I times some angle is essentially just a sine or cosine function. It's a periodic trigonometric function. And we can write our simple harmonic oscillator differential equation as in the usual way, saying the mass times the acceleration equals the minus the spring constant times the displacement, as we would using Hooke's law. Now let's just see what happens when we plug that in there. You get something that looks a little bit complicated, but as we did the first time with the trig functions, we can simplify that. And again, oh look, it's our old friend. We know that this part of the solution has a time in it. So that's going to be varying. So if this is going to hold, we need this other part to be equal to 0 so that it's 0 for any time that we plug in, which means we get our old friend k has to equal m omega squared. Just as we had the first time we looked at this. Now, I should point out, again, if you're a little skeptical that this whole e to the ix thing looks a little weird and wonky, let's remind you, we didn't have to do any derivatives with trig functions. We didn't have to remember any trig identities. This was a lot easier. If you're doing this by hand, using complex functions is a really big improvement because it's just so much easier to work with. The derivative of e to the x is just e to the x, and it makes life simple. And we can always go back to trigonometric functions just by using this relationship. So I can do that. I can actually, in Mathematica, I can just say I want to write out the sines and cosine functions using the complex expand rule. Now, an important point here, because you might be asking yourself, wait, what does it mean to have an imaginary number in my solutions? I don't know what to do with that. You know, can you measure an imaginary number? Well, no, and that's an important point here. So I will emphasize that here, because you want to remember that the solution is the real part of the answer. You can kind of think of this as a mathematical trick, but the only part you care about is the real part. You can basically forget the imaginary part. The imaginary part just comes along for the ride. And all of this is possible because the real and the imaginary parts don't mix. The real and imaginary parts don't mix as long as you have a linear equation. And that's why the linearity of these equations is incredibly important. So I want to show that here and give you, I'll show you that they don't mix. And let me quit my kernel so we can start fresh here. But I want to show you that because we have a linear equation, we can use these e to the ix's, this complex representation. It'll make our lives easier. We can solve problems easier if we're solving them by hand. And it's all because the equations we're working with are linear. So I'm going to rewrite my solution here. I'm going to say, define x of t to be a real part, which could be a function of time, and an imaginary part. So it's a real part A, an imaginary part B, which will be b times square root of -1. Oops. So we're going to define x in that way. So I've got a real part A, and I've got an imaginary part B. Pretty much all of the linear operations, not pretty much, all of the linear operations I can act on x with will keep the real part real and the imaginary part imaginary. So if I multiply by a constant, you can see that doesn't affect anything. Let me expand this so you can see that. All it does is it multiplies a constant by the real part to get another real part. This is assuming we have an imaginary, or rather a real constant that I'm multiplying by. Real constant times real number gets another real number. Real constant times real number times imaginary number gets you an imaginary number. I can also take derivatives. Again, derivative of a real number gives you a real number. Derivative of an imaginary function still gives you an imaginary function. Same thing with the second derivative and the third derivative and any number of derivatives. You still just have your real part up here and your imaginary parts over here. So all of this is because my equations are linear. And if I look at my force function, I have mass times x squared. That's a second derivative. That's a constant. Equals minus k, that's another constant, times x of t. And I don't want to set that equal. I need the double equal sign. Let's just simplify that. Yeah, you've got, well, I guess I don't need to simplify it. This is a linear equation, and all we're going to have is the b's will stay imaginary, the a's will stay the real parts. Where this gets messed up, and this is where you have to pay attention, is when the equation is not linear. So if I graph f equals minus kx, I get a straight line. If I were to put an x squared in there, I would no longer get a straight line. Which means the real part A and the imaginary part B start to mix. So if I expand this, you can see I've got, well, this is real. That's an A. But look, I've also got a B that's real. There's no imaginary numbers here. There's no i's. When I squared it, the i's were squared. I've got square root of -1 squared is just -1. That's real. So a B becomes real. And we've got A multiplied by an imaginary number here. So the real parts and the imaginary parts start mixing. And this is why linearity is important. So you can multiply by constants. You can take derivatives. You can add things. You can linearly add things together, do superpositions. None of that will mix the real and imaginary parts. But as soon as you start squaring things or cubing things or doing anything that's not just a linear, x to the first power, you start running into problems where your real and imaginary parts start to mix. And then you can't really use this trick anymore. You can't just say, I'm going to plug in e to the ix and just take the real part, because the real parts and the imaginary parts are going to get all messed up and intermingle. This video is getting a little long, so we're going to stop here. Hopefully you have seen why imaginary numbers are really useful and why you're going to see them all over the place when you're dealing with differential equations. Hope you liked the video. If you did, please click like. And if you'd like to see more of these, please click subscribe.